And welcome back. Now today we've got two little devices, the two that are shown on the workbench down here, that one there and that one there, and they work very differently to sense current, well, sense and measure current. So we're going to deal with the rubbish one, we're going to deal with the analog one first, and then move over to the good one, the digital one. Okay, I must stop putting my own spin on things. Yeah, okay, no, seriously though, the analog one, which is the one that's connected up currently, and the one we'll be looking at first, I wasn't that impressed with it. It works probably pretty much as designed actually, but this one, the digital one, I think works better. Now I was going to put it through this this load thing at the back. See this big chunky thing at the back here? No, not that, that's the resistor. I want to give a shout out to PCB Way, PCB Prototype the easy way. Just enter the dimensions of your PCB, choose the number of PCBs you want and the layers, and hit the quote now button. Now heads up guys, the voting for the third PCB design contest has already started. The range of submissions has to be seen to be believed. Everything you could ever think of on a PCB. Look over them, select your favourites and get voting now. They depend on you. And just a quick reminder that the May Day holiday is coming up, May the 1st, 2020, but you can always place orders online and customer services is always available. So get voting and have a look at the PCB Way website and try them out today. Right, this thing here allows me to sort of suck current in. It's really for battery testing and load testing of batteries, as well as sucking current in just generally. But actually it stops me testing these to the level that I want to test them. So we'll just leave that for another day and talk that through. Right, okay, now this whole project of current sensing and, well, not so much the measuring, it's really the sensing that I'm interested in, is part of a bigger project. Remember I said my phone project, there was one thing I wanted to do, and that was to sense the current flowing into the phone, actually flowing in, not what the device thinks is happening, but actually happening. And I said we needed to use a shunt resistor and things like that. And I wasn't having the success that I'd hoped I'd have. It was all a bit, well, probably about as good as that one there actually. So yeah, that's probably why I'm thinking it's a bit rubbish. But now, well, let's just look at one at a time, shall we? Let's look at the analog one. Now the analog one is, let me get my browser up and you'll see it. Here it is. Now this is an ACS 712 device. Now it's on a actual module here, so whip back to here. So the chip is on there. So there's the chip, and it's been wired in, you know, to a few components just to make it easy to test. And the current that you're testing goes in here and out the other side, and it's all connected magically inside. Yes, we use a certain amount of magic on this one. Well, all right. A Hall effect, magnetism. All right, sounds like magic, doesn't it? So back to the data sheet then. It tells you everything you need to know about this. This one is the lowest in the range for current sensing. That is 5 amps is what the maximum current it will detect. And therein lies the problem. If you're detecting 5 amps, if you're then going to drop that down in your project to 1 amp, that's a fifth of the range, isn't it? And therefore the fifth of the sensitivity. And if you want to go down to 100 milliamps, that's now a tenth of a fifth. And if you want to go down to 10, well, you can see what I'm getting at. Eventually, because it's analog, this, not digital, eventually the whole signal gets swamped by noise. Or at least in my experience, that's what it's done for the type of current that I'm trying to detect. Right, let's shoot back and look at the thing in action really, and then we'll look at the code, well, at the same time. Right, I've cleared the decks, I've got it all set up, I've balanced this load resistor that the current's flying through from the black and red terminals at the back there on the bottom of my soldering cleaner, that one there, because it gets a little bit hot and I don't really want this plastic mat here to melt, because it does get quite warm even though it's a 10-watt resistor. And into the device, the AC712 module, this is a little module built onto a board. You can get it in all sorts of places. I've got this from Banggood, of course. It's only got 3 wires, so you've got plus 5 volts, ground, the brown, and the yellow wire is plugged into A1 over here, so that's an analog output. We'll talk about the analog output in just a sec. Now, the power that you're measuring from the crocodile clips at the back here, red and the black, it goes through that resistor and then into, or via, I should say, via this green connector, which is internally connected to the AC712 chip here. What goes cut down a couple of these pins, in fact, 2 of the pins are in and 2 of the pins are out. They're sort of paralleled up to let the current flow through, and it's all down to magnetism, the Hall effect. So as the current flows, you get a magnetic field generated, and from that it can detect what the strength of the current flowing is. Right, analog then. So what does this do when this is connected here and no current's flowing? Well, at 0 current, it's half of VCC. Now, if you put 5 volts onto any one of these analog ports, the reading you get inside here from an analog read will be 1023. That's the maximum it can go to, 10 bits. So half of that would be 511.5. So we're not going to get 0.5, so 512, say. So let's whiz over to the code window and just have a look how it's all set up. Now, as you can see, it's pretty complicated code here. There's a lot going. What? 6 lines? Yeah, all right. 6 lines of code. There's nothing going on. All we're doing, well, ignore this bit at the top. That's just the debug output, okay? So we're reading here the analog input from A1. So what I'm saying is, well, if it's bigger than 512, go and print it out. Then have a little delay for half a second. We don't want thousands and thousands of these things popping up, do we? And that's it. So, let's run it and see what happens then, shall we? Okay, we've connected to the port it's on. It says setup's complete, and now we're not actually passing any current at the moment, and yet straight away we're getting this figure coming out. So this is the difference between what we're expecting of 512 and, well, what it says it is doing. And, well, it's wrong, basically. But let me turn on my power supply then, and we'll just see what comes out of there. Right, the power supply is switched on. It's 100 milliamps now. Okay, it's changed a little bit on that output, hasn't it? Over here, it's changed a little bit, but not hugely. Let me up it a little bit more. Right, it's 200 milliamps now. Okay, it's creeping up, but I'm not sure this is really accurate enough for, you know, measurement purposes. Let me up it a little bit more. Coming up to half an amp. Right, that's exactly 500 milliamps now, and yeah, we can see a definite current flow at this point. As I say, the sensitivity of this device is from 0 to 5 amps. So now we've got half an amp. It's a tenth of the overall sensitivity, so it's not going to be a huge amount that it's going to detect. If I disconnect on the workbench, what I'll do is just disconnect that plus voltage here while it's running, and you'll see a huge difference as soon as I do it. So disconnect now. There we are. So it's dropped right down. Now, funnily enough, and ironically, for my purposes of detecting whether or not my phone is connecting and being charged, that would do, wouldn't it? Because I don't think the charger is going to deliver less than 500 milliamps. At least I've not seen that. So this, to me, anything below 100 would be like, no, we're not charging anything. As soon as that phone charger connects, bang, there we are. Look, I can go, yeah, I can detect there's definitely something running there. But to my mind, it's all a little bit hit and miss, really. I think what this really wants is, 1 amp, 2 amps, 3 amps before it really can give you the detail that we want. Okay, we'll just leave it there. As you can see, that has gone up again, but look at the jitter on it. 24, 30, 27. That's noise, isn't it? Because it's analog, and you get this buzz and background noise, and that's because it's picking up other stuff around. Now, in this case, it's not that wire. If I unplug it directly from the board, it does go down to 0. It's this generating noise, basically. And there may be steps to get around that or make it better. And of course, we can have an averaging input. We can put a capacitor on the input just to smooth out those jumps. But the very fact it does do this jumping about, as you can see here now, look, what's it got? It's got 233 milliamps running through there, and it's jumping about all over the place. So as I said right at the beginning, not really good enough for what I want. Okay, let's clear the decks with this. I've had enough of the ACS712. Let's go to something that's a little bit more meaningful. Okay, we've cleared the decks again, and now we've set up the INA219 board. So this is a little tiny AN219 chip on here. That there is the shunt resistor and we'll come on to that in a minute. I'll have to explain that. And it uses 4 wires this time, so you've got plus VCC, 5 volts, ground, and then your I2C wires, SDA, SCL. Now stop. If you're beginning, you go, oh no, I2C, I don't understand how it works. Bear with me, it really is simple, and of course all the hard work's been done. I'm going to show you 2 sketches, so not 1 but 2 sketches. One without a library, the one I initially wrote just by myself looking at the data sheet, and I've got it all working, and then I looked to see if there's a library for this module. Of course there is. In fact, this entire module looks very much like the Adafruit module. So they of course have got a library. I loaded that up. Unfortunately, it didn't really work that well. But the style of the coding, like, I thought, well, if I use the same names they've used, at least the 2 sketches will look similar. Because all I'm interested in, remember, is current flow. I'm not interested about any other values that might be around, but until we've had a look at the circuit, how this works, we're not really going to know. Now, there is a data sheet for this. Here we are. And it's a really good data sheet if you're into data sheets, but you do have to dig a little bit. It took me probably, a couple of hours to work out how to get that current measurement done. So we're not going to go into this particularly. The one thing you do need to know about is that you can go up to 26 volts. Okay, so if you're hoping to measure 30, even though I have to admit I did run this at 31 volts just because I wasn't paying attention really, and when the smoke started coming out of the that big resistor, I turned it down pretty quick, but it didn't seem to damage the device, thank goodness. The other thing it says is yes, you can connect the voltage to this device, the shunt resistor, before you've powered up the device, which is another. Normally it's a no-no. Normally you have to power up your device, then connect other things, and also normally inputs into a device cannot be above VCC, but in this case well above, obviously 26 volts compared to your 5 volts that you're running on, so everything's fine. Now I don't know whether you've got to the message yet that I actually quite like this chip compared to the other one, because there's quite a good few things about it that we can play about with. But before we get into this, and I'm not going to go through this whole data sheet, I mean it just goes on and on and on, and it's really valuable once you've dug into it, but we just haven't got the time to dig into it. Okay, so we're just going to leave that and get my whiteboard out and just very, very, very quickly go over how we're going to measure that current. Okay, so very briefly let's have a look how we're going to sense current. We'll draw a voltage source here in the shape of a battery. So we have a battery, and at this end we have a load. Let's pretend we've got a motor here, right, just for the sake of argument. So we have a motor here. How do we know what the forward current is at this point here? Now normally of course, yes, you'd put a meter in here, wouldn't you? A multimeter or something like that. And it'll go, half an amp, 1 amp, whatever, and you'd know how much current this is taking. But we haven't got a meter to use in this case. What we've got, in fact, is a shunt resistor. And it's a very, very low value. So this resistor, known as a shunt resistor, it's probably 0.1 ohms. That seems to be a fairly standard industry value. Because that low value doesn't affect really the current flowing through all this. The resistance of the motor or whatever other load you got here is probably going to be much higher than 0.1, so it shouldn't affect anything, not significantly anyway. But what we do is take this point here before the resistor and this point here after the resistor, and we're going to feed those in to a op-amp, a comparator in fact. We're going to have that like that. So that's the plus, that's the minus. And the output here is going to be proportional compared to what the voltage drop across here is. And the voltage drop across here depends very much on how much current is flowing. Therefore, the more current that flows, the bigger the voltage drop, and therefore the bigger the reading out here. And now we're talking the voltage drops across this resistor, we're talking in the millivolt range. So we might have 1 millivolts, you might have 10 millivolts. You could even have lower than that, but that's roughly what we're talking about, the voltage drop across here. And this device, I've drawn it as an op-amp, but there's more to it than that. It's clever enough to work out exactly what is happening in this resistor. Now remember, if it knows what the voltage is on here, whatever the voltage source is, and it knows what the voltage is here, and it knows how much current is flowing through here via the voltage drop, it can tell us quite a bit about what's happening in the circuit. So and that is the basis of the INA 219. Broadly speaking, look at the data sheet for much more detail. It's fascinating, believe me. Right, so the general theory of how we're going to measure the voltage drop across the shunt resistor is now clear. Okay, and this chip is obviously purpose designed for doing that. You know, op amp. Well, it is an op amp, but it's purpose built to detect these tiny little millivolt changes. And of course, you've got an I2C interface on it, which makes it so much easier. So what we're actually going to do with this device then, in order to get it to run, let's look at the sketch, and I'll talk you through. Now, don't get put off by all this gobbledygook at the front. What I've done is taken the Adafruit way of describing all these values, and I've put them now into my program as well, rather than using just values or my own names, just to make the two things sort of add up, because I suspect a lot of you will be using the Adafruit library, and I'll show you that in a little while. But what we're actually doing to this device, because it's I2C, is it's an intelligent device, unlike the previous one where it just monitored this analog voltage. This doesn't do anything of the sort. What we say with this one is, oi, INA 219 device, I want to tell you what I'm going to do. And it goes, okay, what do you want to do? And you go, I want to measure the current, please. Oh, okay. Yeah, I now want 2 bytes back from you. For the current milliamps, please. Ah, okay. And you've told it what level of accuracy you want. For example, you can measure 32 volts at 2 amps, or 32 volts at 1 amp, or 16 volts at 1 amp, or 16 volts at 400 milliamps to get the accuracy in the amount of bits it's got. And I think it's 12 bit, isn't it? But anyway, the accuracy that we're looking at can be adjusted depending on what you want. If you exceed the maximum that it can detect, you just get the full scale resolution at that point. So if I set on here, I said, oi, INA 219, I want to measure 16 volts at 400 milliamps. It goes, okay. And then you put 2 amps down the line. It goes, oh, there's 400 milliamps. It's the most I can measure. Sorry, it's 400 milliamps. Maximum full scale deflection on my little internal meter, which is fine, isn't it? You know that you've got at least 400. As it happens, I'm not doing that. I've worked it out and I've tried all the various permutations. I go, do you know what? 12-bit resolution, 32 volts at 2 amps is adequate for what I want, because it's very accurate, this thing. I said, I want you to take a number of readings. I can't remember what I said now. We'll come to that in a minute in the sketch. Take, let's say, 8 readings very quickly, and then tell me what the answer is, so we don't get all that jitter and moving about. What else have I said? There's a couple of other values in here that we set up at the very, very beginning, and from then on it's plain sailing. So let's have a look at this code, and I'm going to skim through it though, because it's sort of self-documenting really. These values that you're seeing at the top here, all these names I've stolen now. Absolute shameless plagiarism from the Adafruit library. So I've given it the same names, the one that I'm using. And you can see here that look, the B voltage range is 32 volts or 16. It depends on what value you put into the configuration bytes as you send them across. But we'll come on to that. And at the top, look, we've got the calibration, the config, and the current registers that we're all using. So this is, this is a clever device. This is a digital device. It's got some intelligence, and you can talk to it properly with I2C. So we're just going to whiz through this. So in the setup, what we're saying is, apart from debugging, we're saying, oi, device, I want to talk to you. And the default address is hex 40, but you can change that to another 2 addresses by soldering little bits on the board. That's blindingly obvious what that is. And then you say, I want to calibrate you, and you send it this number. By looking through the data sheet, it's obvious that it's a fixed number you should be sending it, but it's in 2 bytes. You send the high byte first, and then you send the low byte, which is doubtless going to put off some people, but by doing it this way, it actually makes it very easy. You can say, look, I want to write the high byte here, right? And then I want to write the low byte there. Okay, it's just an easy way of doing it. I'm not sure that Adafruit do it the same way, but it doesn't matter. And then you say, right, this is what I want to do. I'm talking to the calibration register now, and I'm stopping. That's the end of the conversation for that little bit. And then you say, right, another conversation now. Now I'm talking to the config register, right? And you go, these are all the values I'm going to send to you. Now it looks complicated, but believe me, it's not. In fact, I've documented them here. Look, I'm saying, oh, funny enough, I'm on the 16 volt range here. Look. I'm on the 16 volt 2 amp range, which is good for me, for my mobile phone. You're never going to get well, would you get 16 volts even from a smart charger? I'm not sure how high they go up, actually. Doesn't matter, but it's still 2 amp. I want to have the maximum amount of gain on that amplification of the drop across the resistors so I can detect what's going on. I want 12-bit resolution, please, here. 12-bit resolution. I'm saying, yes, I want 8 samples, please. So 8 samples, and it averages them out and sends them back. And yes, I want continuous conversion. So just keep doing this forever, because I don't want to have to tell you every time, oi, go and convert it, now give me the result. It's just like, just keep converting, and I'll just ask you, what's the result? What's the result? What's the result? So it just like on a conveyor belt system, really. And what's the last one hidden there? Oh yeah, that's right. Then we just write once again, just the same as we've done up here. Look, the high byte and the low byte. All right, the high byte we do have to AND with FF, all high bits. Just skim over that. If you think, I don't know what that does, all this is doing is writing the 2 bytes of the config to the register that we've previously spoken about up here, right? The config register. Great, so we've done all that. Then we've got a delay. If you notice on here, I've said I want 8 samples, that's what the 8S stands for, and it takes 4260 microseconds to do all that. So we've got to wait now for 4260 microseconds before we say, let's do the next thing. So we end the transmission for that and make sure that it's all okay. This is a little bit of overkill, I must admit. This is just checking that we've spoken to the right thing and got a response back that we want. That was really an early bit of my code just to check that it was all working. You can probably take that out once you know it's working. And then in the loop, this is the bit that just says, go and get me stuff. We go, oi, I'm talking to whatever's on the end of this hex address, 0 hex 40. So the INA21, I'll go, oh, that's me, I better pay attention. And you go, oi, I want to talk to the current register, please, because that's what I'm interested in. I want the current. And that's the end of that conversation. So the 219 is now going, great, you want to talk to the current register. Okay, I'm ready. Then you say, oi, I want to talk to the device on the end of this hex value here. And it goes, oh, that's me again. Yeah, okay, I'm ready. And you go, on this bit here, I want to have, hang on just a minute, I want to have 2 bytes from you, please. Yeah, okay, that's fine. And then you end it. Right, so the INA219 is really eager now, like a little puppy, going, you want to talk to the current register and you want 2 bytes from me, okay. And then you have a little delay, and then you go, now give me those 2 bytes, please, that I've asked you for, which, as you know, INA219, it's the current register value, the one you've been continuously converting for me every 4,260 microseconds. It goes, okay, I'll give them to you then. So we do a wire read here and move it into the high byte of my integer, the first left, the most significant byte. And then we do a wire read, and that just puts it into the lower significant bytes. And now we have an integer, 2 values, and it makes the whole value up. At which point we print it, and I do have to divide by 10 at this point, because the result of all the configuration that we've sent it means that there's this magic number, unfortunately, and it varies depending on what you want to do. Now I chose 10 because it says that somewhere in the spec sheet. If you do this and it's a Tuesday afternoon in New York or whatever, you have to put 10 in here. So I did, and it works. If you're going to do something else, you probably want to read, well, not just the datasheet library, but the Adafruit library as well. That goes into much more detail on TLDR. I didn't read it all. And then we just delay for 2 seconds and do the next thing. So let's, as you can see over here, nothing's here yet. So let's connect up. I haven't got my power supply on yet either. So let's fire up the Arduino, which is over here now. Look, right. So we're going to connect all this up. There we are. I'm connected. There we are. Current flowing at the moment is 0 milliamps. What do you notice about that immediately? I haven't got my PSU set up. It says 0. Yeah, it's accurate. It's accurate. There is 0 current flowing. So let's turn on my PSU and see what happens. Right, PSU is on, and oh yeah, I've got it down to 0 at the minute. So it's current limiting at 0, and it goes, well, actually 1 milliamp is sneaking through there. So let's turn this up to 10. Now that's 10 milliamps, and it goes, well, actually you've got 11. Now I don't know which is not accurate here. Is it my PSU being a milliamp out, or is it this device being a milliamp out? Don't know, don't care is the answer, because compared to the other device, the analog device, this is like, whoa, it can detect 10 milliamps plus or minus 1 milliamp fantastically well. Now this is current limiting on my PSU at the moment, so that might be another reason why it's probably a little bit dodgy. Let me whap it up to 20, 30, 40. Let's go up to 100, shall we? There, it's 100 milliamps now, and it's saying 101. Great. So my PSU is still current limiting at this point, right? Because I'm still on 5 volts. Let's whack it up a little bit more. My phone charger never delivers 100. It's always more than that. So let's whap it up a little bit more. Right, it's 204, 250 is that now? I can't read it. No, 240, hang on. Right, I've current limited at 250 now. And what does it say? Oh, look, it says here, where I'm waggling my little stick, 250. That's not bad, is it? So I can definitely detect when my phone charger is charging my phone now. Let's whack it right up to, I don't know, 500. 500 now. There we are, 501. There's this one, oh no, it says 500. There's about a 1 milliamp difference, isn't it? Well, actually, it says 500 now, would you believe? And we're still current limiting on my PSU. So, well, I think you've got the point here that this is now an accurate way of interrogating how much current, not just at the big amps, but at the little ones as well. Okay, one final test. I'm going to whack it right up to 1 amp. Right, I've put it to 1 amp, but actually my power supply is saying I can't get that much through that resistor you've given me. It's 757, it says. That's what it's current limiting it to. It's tracking it really well, but these, whilst yes, I do want to detect that it's charging it up to the full 1.3 amps, I think I can get through that phone charger now. Right, there's only one thing left now to tell you where I got all these. You can probably find these modules just about everywhere, and you can of course buy them directly from Adafruit if you want. Well, if you're in the States, getting those in the UK are quite difficult. So where can we get this from? Well, I bought this, as I told you, from Banggood. This is the INA 219. This is the digital I2C one. Absolutely recommend it. It's great. $3.27, which is not bad, except look at this bit down the bottom here. Look, shipping now $2.09. That's to the UK. All the free shipping seems to have gone out the window. Now the analog version, this one here, this is the 5 amp version. It can be 10 amp or 20 amp, and you select that down here, and of course the accuracy goes down. But if you're detecting, I don't know, a kettle, 10 amps, or a lathe, a milling machine, something that has big amps, this will detect it quite happily, and it's a safe way of doing it with the Hall effect. Just that for my particular purpose, this did not meet my needs at all. It just wasn't sensitive enough, and being analog, the noise at the lower end just swamped any signal value that I was getting anyway. But there's a place for this, so you can obviously get that. It's obviously a little bit cheaper, $2.54, but once again, still shipping, and that's to the UK. I suspect it would be to the States and Canada and Australia too. Adafruit library, look, there's code here. This is where I stole all the names from. I'll put links to all this. There's the Adafruit library that you can just download from the GitHub. You probably need to look at some of their examples. There are examples in here. And in fact, the one I took to see how well it worked was Get Current. It's a standard Arduino thing, and yeah, all this here, you see it's showing all different sorts of things. So what it's showing is what's the voltage coming in, what's the voltage drop across the resistor, what's the voltage the other side, how much current is flowing, and what else was there? Oh yeah, what's the power, which it probably just works out, doesn't it? Anyway, they were all pretty well ropey. It just wasn't given me any sensible values apart from the current value, which is the one I got working anyway. So I couldn't really use any of their code to get the other bits working anyway. But I'll put a link into all the Adafruit stuff because I'm sure this must work somehow. It's probably some ridiculously stupid thing I did. I don't know. This is the load. Oh, there we are. Electronic load aging battery power capacity something test module. Okay, so that's the thing that you saw right at the beginning of the video, which we haven't looked at yet. I'll do a separate video on that. I'm going to also do this one here. I've got this one here where this is powered by a 18650, and then you put another one in here and it tells you whether that battery is any good or not. And I've got loads of these batteries and I just don't know the state of them. I suspect some of them are pretty ropey now because they've been reclaimed from machines and things. So I think, is it even worth carrying on with these batteries? Can I just chuck them? So I've got this to tell me the answer, I hope. So we'll talk about that one at the same time. Okay, that's about it, I think, for this week. Yep, everything's done. I think we covered all the topics. Thanks very much for watching. Next week you'll be looking at a totally different sort of video from me, so stand by for that. Be on your guard. Okay, all about SMD soldering, but it's a bit different to what I normally do. Comments down below, and if you like this video, give it a good old thumbs up. See you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.